Okay, hello everyone, and thank you for attending this presentation. Thank you very much for the pharmacometrics study group. That's really a great initiative. So I'm Marshall Viel, I'm from INRIA, and I'm also part-time professor at École Polytechnique. So I will be happy to present the mlxR package. So it's a package for the simulation and visualization of models for longitudinal data, of course, including PKPD models for continuous categorical count time to event data models. Also, you will see that it's possible to include some individual variability in the model, and then to perform clinical trial simulation, and also to integrate this tool in a modeling and simulation workflow. So mlxR is developed by INRIA for the TDMOR project. And there is an extensive user guide online here. Just here, have a link. Let me just show you that quickly. Oops, it is. So I will not present everything, but you have a lot of detail about all the features, what is available, the type of model that you can use. And always, let me just open one. For example, the page about time to event data model. You will find some introduction about the models, really the mathematical description of the model. And then you have some examples with the R code, etc. And what is important is that for all these examples, all these demo examples, you can download the R code and the model also. Okay. There are several case studies where you have more complex PKPD models, for example, TMDD models, a lot of example of clinical trial simulations as well. There are many Shiny applications. The combination of Shiny with Simulink with mlxR is really very powerful. And you can look at that. Also, what is important is that for all these Shiny applications, any of them, you have access to the code. That is to the R code for reproducing exactly the same Shiny application. Okay. And you have some detail about the installation also, but not too much about that. Just need to install first a C++ library because it's really much powerful, much faster if you use this powerful C++ ODE solver, for example. So there is a link for that. And you can download and install the package from Crown or from GitHub. There is the working version is on GitHub. Okay, just want to move that. Okay. Okay. So mlxR is a package with several functions. The main function with the Simulix. But I will start with a PK model, which is very useful for computing some very basic PK models. So I will switch now to R. Okay. And I will go directly to an example because you see it's quite easy to understand how it works. See, it's very flexible. It works like a PK library where you can very easily implement more than 100 basic PK models. So this is a first example. And the idea of PK model is that the model itself is defined by the name of the parameters. So that avoids to have 100 functions. You always use the same function, the PK model function, but according to the name of the parameters, then a different model will be defined. So in this first example, the parameter are the volume, V, the clearance, CL, and transfer rate constant between peripheral compartment and the central compartment, K12, K2. Of course, these are keywords. They are reserved keyword, and there is, if you go to the website, oops, here on the page about PK model, you will find the list of the reserved keyword that can be used. So you see that you have, example, for transit compartment, MTT, R, TLAG, etc. VMKM for nonlinear elimination, etc. So that's very, very flexible. In this example, we want to compute the predicted concentration between time 0 and time 30, every 0.1 hour, for example. And we need now to define, of course, the dosing regimen. So in this case, we give 40 units, 40 milligrams, for example, at time 0, 14, and 20. And that's enough for a PK model. So I will just run that. What I will do, and during this presentation, I've prepared some R code and just ran all this the script. I don't want to spend too much time typing all this instruction. So now I can run PK model, and the output, it's a data frame. It's a data frame with the predicted concentration at the time that you have defined. Okay, so then you can use any R package, R function for plotting data. I'm using a ggplot here. So here I'm use ggplot just to display the predicted concentration as function of time. And now that's very flexible. You can very easily modify the administration schedule. For example, I can add dose at time 8 and then run it again, plot it again. I can, for instance, assume that it's now an infusion. So I can define an infusion rate using the keyword rate, for example, 10 milligrams per hour, etc., etc. So that's very easy to use. So this is a simple model. You can imagine to have more complex model. As I said before, you can, this model, it's a model for oral administration, but assuming now that we have some transit compartments. So MTT is the mean transit time, okay, and KTR, it's the transition rate constant between the transit compartments. So then we have Ka, which is the absorption rate constant, volume, and VMKM are the parameters of the Michaelis-Menten elimination. And you can also assume that you have only a fraction P, which is absorbed, for example, the value of ability. Okay, so that's completely defined the PK model. Now I define the dosing regimen. And you see that we can have different amounts of drug given at the different times. It's not necessarily the same amount. So I run this one, the parameter, I define the administration, then again the time, here it's between time 0 and 80, and again I use PK model to compute the results, the predicted concentration, and plot okay, the predicted concentration. And again, you can modify anything, you can change the in-transit time if you want, and then run it again. This is for only one single subject, of course, but you can use PK model for several individuals. Here, I'm using a very simple model, a one compartment model for oral administration. But I assume that I have 3 IDs and 3 individuals now with different dosing regimen. So this function inline data frame just to create a data frame easily. So if I run that, then ADM is a data frame. Okay. And what you can see that we have 3 IDs. The first ID receives 2 doses at time 0 and 12 with different amounts, 40 and 80 milligrams. ID2 receives only one amount, one dose at time 3. And ID3 receives 2 doses at time 0 and 8. Okay. So I will now compute again the concentration at time 0 and 30. But now I will plot predicted concentration, different colors according to the ID. So you see that I have my 3 IDs. So here, in this case, the 3 individuals share the same parameter, the same PK parameters. You can also assume that you have different PK parameters. So here, again, I will define param now as a data frame instead of a vector. So you see that param here we have different Ka, volume, and clearance for the 3 individuals. Okay, and then I can again compute the predicted concentration for the 3 individuals and plot for them. So we have now different dose regimens and also different PK parameters. Okay, so that's great when you have some, as I said, some basic PK models, but here there is no variability, there is no residual error, and the model are basic PK models. Now, if you want to implement a more complex model, of course, you will need to write your own model. So that's what we will do now using the function Simulx instead of using a PK model. Simulx, really the main function of the package, and it's much more flexible, of course. So Simulx can be used with model implemented using mlxR. mlxR is the model coding language used by the Monolix suite. I will say a little bit more after that. It's also possible to use a model implemented in R, but that's much more tricky to implement, and that's very slow. The ODE solver, in comparison with the C++ ODE solver implemented in mlxR, it's really extremely slow. It's also possible to use a FarmML model. It's FarmML models. FarmML is the markup language developed for the DDMore project. So let me show you just a first example. In this first example, I will consider a model for oral administration, okay, but with a combination of linear and non-linear elimination. So there is no model in the library for that. So you will need to write your own model. Okay, so here it is. So the first thing to do is to write the model, the PK model, before using R, before using a Simulx. So you have 2 options. You can or define the model inline, really in the R code. This is what I'm doing here. I will explain after what it means. Or you can use an external file if you have your own library, for example, here. So it's a text file. Let me show you. Here is the model. It's a text file, but it's exactly the same information, the same syntax, everything. It's exactly what you have here. So these two options are absolutely equivalent. When you define the model is inline, you have only one single R code, R file. Okay. On the other hand, here you have an external file, so you need to take care with, of course, with the path, etc. You define some relative path. So how does it work? You have first the system of differential equation. Here it's a dynamical system, a Pick model, a dynamical system, which is mathematically represented by a system of differential equation. So you have here the depot compartment, the amount in the depot compartment, and the depot and the amount in the central compartment. And we have a linear transfer from the depot to the central compartment. And we have a combination of linear elimination and nonlinear elimination from the central compartment. And then we define the concentration from the amount. So this is the model. Okay. And now what we say is that here in this PK block, we just say that the target is the depot compartment, which means that it's a model for oral administration, of course. So now the model is ready and can receive any doses. So this is what we will do, exactly as we did with the PK model function. It's very similar now. We define an administration, some doses. Here, for example, 50 milligrams are given every 24 hours, starting at 0. Okay. So let me just run that. Now I define the treatment. Okay, so if you look at the treatment, it's a list with the amount, which is here a scalar because it's the same amount for all the doses, and then we have the time of doses. Then we give some parameter value, of course, and the parameters need to parameter defined in the model. That's absolutely mandatory, of course. And then here, it's not, there is no reserved keyword. You can absolutely what you want. And then you define what you want to do with the model. Here, I say that I want to compute CC, predicted concentration, okay, between time 0 and 2. But I could also select AC, AD, the amount in the depot, any variable that you have defined in your model, used as an output. Okay. So I run now Simulix. Okay. And res is a list of data frame. And one of the data frame, of course, is CC, because this is what we wanted to compute. Okay. So again, CC will be a CC computed between time 0 and 200 every 0.2 hour. And then you can plot that. Okay. Now, of course, if you want to change the value of Ka, you can do that. And you can, let me put Ka equals 1, for example. You can run it again. Okay. And plot again the new predicted concentration with this value. So you can modify easily anything. If you want really to play, to visualize, to perform some sensitivity analysis, explore the model, that's not very convenient. Maybe you want to have something more interactive, more user-friendly. So for that, we have developed this function, Shiny MLX, which creates a Shiny application directly from the input of Simulix. So how does it work? You have here the input of Simulix, okay? But you can use exactly the same inputs for this function, Shiny MLX. So we need a model, we need, of course, the treatment, the dosage, some parameters values, some initial values, and what we want to display, what we want to compute. So if you run that, it will create automatically a Shiny application. Okay? And then you can plot, if you run this Shiny application, just enlarge that. You can play with the parameter value and see what is the impact of Ka, etc., etc. What is the impact of K on the linear entrance, etc., on the amount, just to see that have some non-linearity in the model, some saturation in the elimination. Okay. So that's really very, very easy, because you just need to use this function Shiny MLX. There are many options. Of course, I was using the default, but you can customize your Shiny application. I will just show later another example. We create a dashboard, or complex dashboard. Now, you can also use, Simulx can be very useful if you have now a combination of different types of administration. Imagine that you have a combination of IV and oral administration, for instance. Okay. So I will do exactly as before. First, I write the model. Okay. So here, the model is meaning the same model as before. So we have here, oh, no, it's not a Michaelis-Menten elimination. It's again a combination of linear and nonlinear elimination. So the model is exactly the same, the dynamical system, and the system of differential equation is the same as before. But now, instead of only one type of input of doses, we have two types of administration. So when an administration is of type 1, the target compartment is a depot compartment. That means that it's an oral administration. And furthermore, we can assume that only a fraction f is absorbed. So this is really, in this case, the bioavailability. And when the type is 2, the target is the central compartment. It's an IV administration. And again, now the model is ready to receive doses. We just need now to specify the type of the administration, just to say if it's oral or IV. So this is now our code. This is how it looks like. So here I define a first administration of type 1. So if you remember, that means that it's an oral administration. And we administrate 100 milligrams, for example, every 12 hours. So just run that first. So this is my first administration. Then I have another type of administration, which is an IV now administration, because it's soft 2. And furthermore, it's a perfusion, because here, this is the time of infusion. It's a reserved keyword, inf equal 2, so it's 2 hours. Okay. So I define now this administration. Again, just need to give some pk, some value for the pk parameters. The output is again the central, the concentration in the central compartment. And now the treatment is this combination of TRT1 and TRT2, in that we will combine oral and IV administration. If you do that, if you plot again the predicted concentration, this is what we get. You see that we have this oral administration every 12 hours and the IV infusion every 24 hours, starting time 6. Okay. Now you can imagine that you want now to compare different combinations, different treatments. For example, what happens if now I, instead of using this IV administration, I replace the IV administration by an oral administration. So I define another type of administration, but now it's exactly the same, but this one, but instead of type 2, it's not an IV administration, it's type 1. So it's an oral administration. Okay? Now I can create two different combinations, two different treatments. One is a combination of TRT1 and TRT2, so oral and IV. And this one is a combination of the two oral administration. And now this new input argument group means that I will create two different individuals. I will consider two arms, if you want. And again, now if I plot that, and if I use different colors for my two groups, for two individuals, then I can compare automatically the two predicted concentration. So that's really very, very flexible. You can combine many, many different types of administration very easily doing that. Okay. Now let's move to the next example. Because of course, Simulx is not only for PK models. You can combine, you can link PK to PD models or time to event models as well. So this is what we will do in the next example. Here, oops, here it is. Okay, so I have here now a more complex model. It's still a structural model, and it's just a set of equations. But now I have a model. Here I'm just using a model from the library for oral administration with mechanism and elimination. I link this PK model with a PD model. So here I'm using an indirect response model. It's an IMAX model. Okay, so it's here a differential equation again, which define E. And this is the initial condition, the way that we define the initial condition. And then I can also link that to a time to event model, to survival model. So here H will be the other function, and I assume H is function of the effect. Okay, so it's just an expansion model. And the survival, I compute the survival from as a function of the hazard, just as an exponential of minus the integral of the hazard. So I have now three interesting functions: the predicted concentration, the predicted effect, E, and the predicted survival. Okay. Now, again, that I define then, again, the treatment, the same as before, 50 milligrams every 24 hours. I have now PK model, parameters for the PK model, for the PD, and for the time to event model, with different values, parameter values. And now the output will be the predicted concentration, predicted effect, and predicted survival between time 0 and 200. Now I can use a Simulx exactly as before with that. But now, of course, if I look at this in the output of Simulx, I have now several data frames, the predicted concentration, CC, E, and S, and also the treatment. So I can now use ggplot to plot the CC, plot E, S, and then display the three predictions on the same. Okay. As before, if now I want to play with the parameters just to see what is the impact, for example, of the dose regimen on the survival, instead of changing the value and running Simulx each time, I may want to use a Shiny mlx. This is what I will do. To create a Shiny application. So here, this is I will just use CC and S, the predicted concentration and the survival as output. I will define here again the treatment, the dose regimen, but using another parameterization, because these are reserved keywords. TFD means time of first dose, number of dose, the interdose interval, and the amount, of course, because you will see that now it will be possible to modify that interactively with your Shiny application. So here, so this is again a Shiny MLX with the same inputs, but here I'm just changing the style. This is one of the possible, one of the options. You have several styles that you can use, and here I'm using a dashboard. I run it. Okay, so you see you have this dashboard. Now, since I have defined the input parameters as a list of 3 vectors, I did that because I wanted now to have my Shiny application different tabs for the parameters. I don't want to have a list with many sliders. I prefer to have tabs just to navigate between the parameters. Again, of course, I can modify any value of the parameter, but what is interesting is to define a reference profile. If you click on ref, then you will define, you can then modify, for example, I don't know, PM. So you can see what is the impact on the predicted concentration, but you have always this reference. You can reset this reference if you want. And now what I said is that since I'm using this parameterization for the dosing regimen, I can now play with the first dose, with the number of doses. What happens, for example, if I reduce the number of doses? So you can see here, of course, the predicted concentration now after the last dose, and you can see how the survival, the predicted survival, really decreases significantly after when the concentration goes to 0. That you can also see what is the impact if you change the interval dose, etc. It's like or the amount if you increase the amount. And again, you have all the code here, which are available. So you can, you can play with that, modify. This is something which is, oops, sorry, it is. That's very easy to create that because you just need one line. Okay, but then you have access to the R code and play and modify, of course, the Shiny application if you want. Okay. Let's move to the next example now, because for the moment there is no variability. It's completely deterministic. And one of the interests, of course, for clinical trial simulation is to introduce some randomness, some variability in the model. So first, you can introduce some inter-individual variability on the parameters first. This is what we will do. Next example. So I'm still using exactly the same model as before. It's the same structural model. But now, instead of considering just one parameter value for all these parameters, I will assume that all these parameters are random. So I have in my model now an additional section, which is individual, where I will define the probability distribution of my parameters, of my individual parameters. So here I'm using log normal distribution for all the parameters, except Imax, which has a logit normal distribution. It's supposed to be between 0 and 1. Okay? So now the inputs of the model are the population parameters, KA pop, and all the omega. Okay. So the model is really a hierarchical model. And first, you define the distribution of individual parameters, and then you can compute the predicted concentration, effect, survival, etc. Okay, so let me just do that again. So I define again the same dose regimen as before. I will not change that. Now the population, the parameters, as I said, are the population parameters. Okay, and the predicted here, the predicted value are just the concentration, predicted concentration, and survival. This is what I will use. And now, instead of one single subject, the shiny application. Okay. Instead of one single subject, now I want to simulate 5 individuals. Oops. Just do it like that. Okay, yeah. Now, if I look at, for example, one of the data frame, the predicted concentration, CC, see that I have now the predicted concentration, but for ID1, and I will have, of course, the predicted concentration for all the ID until ID5. And then you can plot that using different colors, as you see. So they have different individual parameters. So of course, the predicted concentration, the predicted survival are different. Now, if you want to do that with a large number of subjects, for example, 500, maybe you don't want to let me just compute that first. You don't want to display the 500 predicted concentration or survival. You will not see absolutely nothing. But what you can do instead, you can display the predicted distribution of the concentration of the survival. So there is a function in the package, which is called PRCT mlx, just to display some percentiles or some quantiles of the empirical distribution. So I will use it here. And I will display, for example, the predicted distribution of the survival. So it's S, and you see that you have automatically a different prediction interval. Here, the default is to use the different decile. So this is the 10th percentiles, 20, 30, 40, the median, etc., etc. And you have several options. For example, you can modify the number of intervals and also the level. So if you have here, if you have only 2 intervals, 2 bands, and the total level here, it's a 50% prediction interval. But you can now say, oh no, I just want one prediction interval of level, for example, 90% prediction interval, only one. So that's important because this is really the prediction, the distribution of the survival. So you really visualize the impact of the inter-individual variability of the survival. Now, it can be interesting to compare. We are moving toward clinical trial simulation. So we can now compare different treatments, for example. We want to compare 50 milligram and 100 milligram, for example. So I define 2 treatments, and I have now 2 groups of size 500. And now I can do the same and simulate my data with these 2 groups, and then plot the predicted concentration in group 1, predicted concentration in group 2, predicted survival in group 1, and predicted survival in group 2. Sorry. Here you can now really compare what is the predicted concentration, and this is really the exposure, the true concentration in the body, the central compartment. Now there is this is just what is predicted by the model. There is no observation at all for the moment. Okay, so that will be the next step. To say that now we will assume that we have some observations, some measurements that can be observed concentration and events, for instance, not only predictions. So let me show you the next example. So I'm using again the same model as before, the PK model, the PD model, and the hazard. But now I will define some random variables, which are the observed concentration. I'm just saying that they are normally distributed around the predicted concentration. And the standard deviation here is B, which is B times CC. That means that I'm using here a proportional error model. You can use absolutely what you want. It's extremely flexible. And for the events here, I define E, okay, which is a single event. I will simulate only one event, it can be death or anything. There is a right censoring time, which means that, of course, the study ends at time 200, and then we don't know what happens. And the hazard is defined here. So that's enough to define the model, the complete model. And again, as I did before, I will put some interpatient variability on all the parameters. Okay. So let me do that. Again, I define the treatment, the same as before. I provide some parameter value. And now the outputs are the predicted concentration, but also the observed concentration, observed event. And this is what I will run. Oops. What should I do? Oops. First I need to click. Okay. And that. Okay. And now I can plot, for example, the predicted concentration and the observed concentration together. And I can also display the event for this subject. You can see here that for this subject, well, we did not observe the event during the study because it's right sensor. Since at time 200, we have not observed yet the event for this single subject. Now, this is for one single subject. That's not very useful. And for clinical trial simulation, and this is now what we will do, and we will really simulate a clinical trial, always with the same model. So this is my model for joint PK and time to event models, assuming some inter-individual variability. But now I will consider a group of 100 patients. Okay, and they all receive the same treatment. I can do the same as before. I now use simulate my 100 patients. But now, if I want to display the events, okay, I can display the empirical survival function, that is Kaplan-Meier plot. So there is a function, km plot mlx, which will display the Kaplan-Meier plot. So here it is. See the empirical survival for this 100 patients. You can see that there is right censoring at time 200. You can add, if you want, a confidence interval, a 90% confidence interval, for example. And that's easy to extend if you have now, instead of one single arm, now I can compare my two arms as I did before. So the second arm, we will administrate now 100 milligram, again to 100 people, 100 patients. So this is the simulation, and now I can again plot the Kaplan-Meier plot, and you can see that now you can compare the Kaplan-Meier. Now, of course, if I repeat that another simulated trial, so of course the result is different. Repeat again, it will be different. For each simulation, of course, it's different. So it really depends on the simulation. So what will be interesting, that what I will do now, it's instead of simulating a single trial, I can simulate a lot, many replicates, and just to see a little bit what happens in average. So that will be my next example, mlx6. So in this experiment now, in this example, what I want to do is to compare first a different group size, 25, 50, or 100 individual in each arms. I want also to compare different amounts of drug, 0, no drug, 25, 50, and 100 milligrams, for example. Okay. But instead of one replicate, I will now simulate 100 replicates for each combination. And my outcome of interest, my endpoint of interest will be the survival at time 100 and 200. So what I will compute for each replicate will be the rate, the fraction of patients, for example, still alive at time 100 or time 200. So this is what I want to do. I'm still using the same model as before. So this is, I just run that, and I will say a few words while it's running, because of course now I'm doing, you need to code a little bit. It's not very complex, because you need to do some loop over the different amounts, over the different group size. Okay. And then each call of Simulx will be for a given group size, for a given amount. But there is this additional input argument, which is the number of replicates. That means that now I want to perform M100 replicates. So at the end, there are 12 combinations, 100 replicates for each combination. So it's 1,100 replicates, and you see on 30 seconds on this computer, on this laptop. So it's very fast. So you can really perform a lot of simulation very quickly. And once you have done that, of course, now I have all this survival for each combination. Then you can, for example, use ggplot to display some box plot. Not display that, and this is just to display some box plot. But you can now compare the survival according at time 100 and time 200 with different group size, just to see that how the distribution is different. The viability decreases, of course, with the size. And you can check also that, of course, the survival improved when you increase the dose. Now, if you're, imagine that you have a decision rule to decide to continue your study if, for instance, you have an improvement of the survival of 10%, for example, with respect to the placebo. So if this is your condition and your decision rule, you can now very easily perform some statistical tests. So this is my solved. And we can compute the power of the test, that is how many times you will conclude that your drug is efficient enough to continue. So of course, the power increases with the amount and with the size of the group. Okay. So yeah, that was a quick overview. I think I have some other example, but I will stop now. As I said, you will find many examples on the website. So just there is yeah a question about additional requirements C++, etc., in addition to the R package. So here in the installation, as I said, if you want to use this mlx library, which is a library, you can install the monolith suite directly from here. And so it's completely free for academia, and you can ask for an evaluation license otherwise if you want. So it's available for Windows 64, for Linux, or for Mac. And you just need to install the suite, and then automatically you will have access. It will be linked to mlxR, to the package. Okay. Yeah, I think that's it. And thank you very much. And I hope that you will enjoy mlxR. If you have any question, I will be happy to answer later. You can write me an email. Thank you. Bye-bye.